This video will be about binomial radical expressions. So when you're working with a binomial radical expression, first we have to worry about what a radical means. So when you have a radical, there are certain parts to it. The first is the index. If there's a little number in front, then that is called the index. And then if you have something inside, that is called the radicand. So on an expression that doesn't actually include an index, you always assume the index to be 2. That means we're taking the square root. So like square root of 4, we're trying to decide what number multiplied by itself 2 times equals 4. Well, that is 2, because 2 times 2 equals 4. If we have a 3 in the index spot, that means we're looking for a number multiplied by itself 3 times that would equal the radicand. So since 2 times 2 times 2 equals 8, the cube root of 8 is 2. If it doesn't come out nicely, that means you'd end up with a decimal. If we had like square root of 5, that would be some decimal. You'd have to plug it into a calculator to know for sure. So first, with binomial radical expressions, we may need to add or subtract some expressions. The only way you can add or subtract a binomial radical expression is if they have the same index, and both of them being blank means they do have the same index, and the same radicand. The index and the radicand must match before you can combine them. If they do match when you combine them, you just combine the numbers in front. 5 minus 2 is 3. We leave the index and the radicand alone when we're combining with addition or subtraction. So the answer to this problem would be 3 square root 3. So what about this next one? We check and the indexes match, but when we check the radicands, they are not exactly the same, so they do not match. That means this one is not possible, or they could say simplified as much as possible. It's not possible to do anything else, or they can say it's already simplified. Sorry, should have an IF in there. Simplified already. So looking at this problem, square root of 72 plus square root of 32 plus square root of 8, you may assume I can't do these, the radicands don't match. Before you can assume that, you've got to simplify them as much as you can, and then see if they could add or subtract together. So to simplify these, we're going to need a list of our square roots. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, and square root of 36 is 6. Usually you need a list all the way up to 15. It's a good idea to have one of those handy. I know we're not going to need any higher than this for this particular problem. So now we have to split up each of these, and specifically we want it to be split up so that we have square root of one of these perfect squares. So I want square root of like 36 here times square root 2, because 36 times 2 is 72. So I'm splitting 72 up using multiplication. Specifically, I wanted to use a perfect square though, because now once it's split up, I can do the square root of 36 to get 6. So 6 square root 2 would be the square root of 72 simplified. Okay, what about square root of 32? The closest number is square root of 25, but if I tried that, there's nothing that would work to multiply 25 by to get to 32. So square root of 25 didn't work because there's not a number I can multiply by 25 to make a 32. So let's try 16. Is there anything you can multiply 16 by to make a 32? Well, 16 times 2 is 32. So again, now I can simplify each piece individually. Square root of 16 is 4. Square root of 2 we can't simplify anymore. That would give us a decimal, so we have 4 square root 2. And then it's still a plus because we originally had plus up above. Next we look at 8. Let's try 4. Well, 4 times 2 again would give us 8. So according to our chart, square root of 4 is 2. So we get plus 2 square root 2. So now we check all our indexes match. They're all blank. All our radicands match. They're all 2's. Now I can add all these together. 6 plus 4 is 10, plus 2 is 12. And then we leave the radicands alone. This would also work for cube roots. So if you had a cube root, let's make a chart for our perfect cube roots. Cube root of 1 is 1. Cube root of 8 is 2. Cube root of 27 is 3. Cube root of 64 is 4. Again, you could keep going. Usually we don't need to go as high with our cube roots though. So looking at this, notice the first one, cube root of 27, it's on our list. We already know the cube root of 27 equals 3. So to simplify this one, we just know it's 3. It's on our chart already. Second one, we have 5. Now really there's a multiply sign here, even though they haven't written it. 5 times the cube root of 32. Well, we again want to see what multiplies to be 32. Has to be a number smaller, so it has to be either the 8 or the 1. So is there anything we could multiply 8 by to make 32? Well, I can multiply 8 times 4 to make 32. We do still have the plus sign in the 5, but now it would be 5 times 2, because the cube root of 8 is 2, times cube root of 4. Cube root of 4 is not on the list, so we have to leave it as cube root of 4. Then last one, 54. Sorry, is not what I wanted to write yet. I want to do the multiplication part first. So things that multiply to be 54. Let's start with the 27 and see if there's anything that multiplies to be 54. Well, 27 times 2 is 54. So we have minus 3 times the cube root of 27 is 3 times cube root of 2. So now I do that multiplication out front. 5 times 2 is 10. Cube root 4 minus 9 cube root 2. And now we have to check our indexes and our radicands. 3 doesn't have an index or a radicand anymore, and there are no other numbers without indexes or radicands, so that can't combine with anything. Our 2 radicals have the same index, but different radicands. So if nothing matches up, we have no like terms. That is as simplified as we can go. That is our final answer. So one last problem. 3 plus 10 cube root of 16 minus 9 cube root of 2. Now in this problem, I'm going to show you a second way to simplify these, just so you have some options. If you don't like using the list of perfect squares and perfect cubes, there is actually a second way. Instead of specifically looking for something that multiplies to be 16 that already is a perfect cube, I'm just going to look for any numbers that multiply to be 16. So like 4 times 4. That multiplies to be 16. And I'm going to keep breaking it down. 4 I can break down to be 2 times 2, and the same thing with the other 4. So anything that I have broken down is not used anymore. So we're left with 2 times 2 times 2 times 2. Now this is where the index would come into play. Since the index is 3, we are looking for groups of 3. We want 3 of a kind. We have 3 2's here, and what that will mean is when we go to simplify, again we still have the plus 10, but that is just from above. So when we go to simplify, anything that's not part of the group stays in the radicand. Anything that is part of the group, we get rid of all but 1. We're only going to keep 1 of the 3 of a kind, and that's what comes outside of the radicand. So that's a second option. If you don't like that option, stick with the first option. You have choices. So now we can do 10 times 2, which gives us 20, cube root of 2. Now I just kind of skipped over 9 cube root of 2. I should explain why I skipped over it. If I try and break down 2, the only thing that multiplies to be 2 is 2 times 1. We never want to factor if there's a 1 involved, at least when we're doing radicals. So since it was 2 times 1, this was already as simple as it could be. So looking at our radicals, we do have the same index and the same radicand. So just the last 2 terms will combine. 3 cannot add to any of it because it does not have the same radicand or index. But we can do 20 minus 9 to give us 11 cube root of 2. So next we can do multiplication. So when we are multiplying 2 radicals that are binomials, first we have to remember the process to multiply something like this. This is called the foiling process. We will do the first times the first, and that's what F stands for, is first times first. Then we would do outer times outer. So first times first is 2 times 5, which is 10. Then we do outer times outer, 2 times square root 3, which is just plus 2 square root 3. Then we do inner times inner. So O stood for outer, I stands for inner. That would be 3 square root 6 times 5. When we're multiplying, you kind of have to multiply like terms only. The 3 and the 5 can combine because they don't have radicals. So that becomes 15 square root 6. And then last times last, 3 square root 6 times 3, or square root 3. Now we can multiply the 6 and the 3 together this time because they do have radicals. So now we need to simplify anything that will simplify. If I try and break down 3 times 1 doesn't work, so we move on. If I break down 6, 2 times 3, 2 would be 2 times 1, and 3 would be 3 times 1. But since our index is 2, remember if no index is written in, then there's a 2 there. We would be looking for groups of 2. We would be looking for 2 of a kind. They don't match. There are no groups of 2, so that one doesn't simplify either. Then 18, we have 3 times 6, and then 6 breaks down again to be 3 times 2. 6 is no longer used because we broke it down again. So we have a 3, a 3, and a 2. We're looking for groups of 2. So altogether we have 10 plus 2 square root 3 plus 15 square root 6 plus 3 times, we get rid of all of them except 1. So a 3 would come outside the radical with a 2 left over. Remember, the second option would be to do square root of 18 is square root of 9 times square root 2, and then the square root of 9 is 3. So that would still give you the 3 square root 2. So let's simplify that now. Three times 3 is 9. So checking all of our radicands are different. That means this one is simplified as much as possible. That is our final answer. So the last topic in this section is, here's another multiply problem. I forgot I had a second multiply problem. I wanted to do this one just because we had the cube roots involved. So we still do first times first. 5 times 5 is 25. Outer times outer. 5 times negative cube root of 4, which would just be 5 cube root 4. Inner times inner. Positive cube root 4 times 5, which would still just be 5 cube root 4. And then cube root 4 times cube root 4. You do not multiply the indexes. It's still going to be cube root. But you do 4 times 4 is 16. Now notice, these middle terms are exactly the same. They're going to actually cancel each other out. So all we need to simplify is the 16. 16 is 4 times 4. 4 is 2 times 2. And we're looking for groups of 3. We get rid of everything except one of them. So we have minus 2 cube root 2. We still have the 25 in front. That is as simplified as we can go. Now it does talk about special cases on the lesson in GradPoint. I prefer to just do it the same way every time instead of having to remember all those different special cases. There are cases where you can recognize, hey, this stuff is going to cancel, and you can skip multiplying that out. I prefer just to do it the same way every time. So our last one is division. Now 1 over square root 2 looks simplified, but according to mathematicians, they do not like radicals in the denominator. This square root 2 being on the bottom of the fraction is a problem. So we have to multiply by something in order to get rid of the square root 2 on the bottom. We call this something a clever form of 1. We're going to have the same number on top and on bottom, and the way we pick it is by the denominator that is already there. I'm going to use that same denominator, and this will end up simplifying. Here's why. If we do 1 times square root 2, we just get square root 2. But if we do square root 2 times square root 2, we get square root 4, which is a perfect square. If you multiply a number by itself, it's going to automatically make that perfect square. So you go back to your list of perfect squares. It's a couple pages ago. Square root of 4 was 2. So we get square root 2 over 2. This is considered simplified because we do not have a radical in the denominator. It gets a little more complicated when you have a binomial in the denominator. We can't just multiply by 1 plus square root 5. This time we have to make a slight change. We're going to multiply by something called the conjugate. The conjugate looks almost exactly the same, except you change the sign in between the two numbers only. So we're going to multiply by the conjugate, which is 1 minus square root 5. Now when you do this, we have to kind of pretend that there were parentheses here already. Each fraction has its own parentheses, or each part of the fraction has its own parentheses. But now we just distribute or FOIL like we practiced with the multiplication. Here I would have to do 3 times 1, which is 3. 3 times negative square root 5 is negative 3 square root 5. Here we're going to have to FOIL. 1 times 1 is 1. 1 times negative square root 5 is minus 1 square root 5. Inner times inner. Positive square root 5 times 1 is positive 1 square root 5. And last times last, positive square root 5 times negative square root 5 is negative square root 25. So the reason we chose that conjugate is because now these middle terms will cancel. And we can also recognize square root of 25 as a perfect square. The square root of 25 is 5. So now we simplify, we'd have 3 minus 3 square root 5 all over negative 4. So one last example. We're still going to multiply by the conjugate of the denominator. Remember, it's always based on the denominator. So we have negative 2 minus square root 3 over negative 2 minus square root 3. Again, we only changed the middle sign, not the first. Now we're going to have to FOIL on the top and the bottom of these fractions. Since the top already had two things, this turns into a FOIL problem. 3 times negative 2 is negative 6. 3 times negative square root 3 is negative 3 square root 3. Excuse me. Square root 3 times negative 2 is negative 2 square root 3. And square root 3 times negative square root 3 is negative square root 9. Over. Negative 2 times negative 2 is positive 4. Negative 2 times negative square root 3 is positive 2 square root 3. Positive square root 3 times negative 2 is negative 2 square root 3. And positive 3 times negative 3 is positive square root 3 times negative square root 3 is negative square root 9. Here, we'll have these cancel again. That's the whole purpose of our choice of the conjugate, is because those middle things will cancel. On the top, we'll have some things combine. So we'd have negative 6 minus 5 square root 3. Because the indexes matched and the radicands matched, we were able to combine. And then square root of 9 is a perfect square again. Square root of 9 would be just 3. Or you could go break it down. Square root of 9 is 3 times 3. It's as much as we can break it down. That's the only group of 2. So in our radical sign, there's nothing left over. One of them we get rid of, and one of them goes to the outside of the radical sign. If there's nothing left in our radical sign, we just get rid of it. So that's a second reason for why this is just 3 now. Same thing on the bottom, we have square root 9, which is 3. Now on the top, negative 6 minus 3 is negative 9. Those are like terms, so we can combine them. But minus 5 square root 3 doesn't have anything else to combine with. 4 minus 3 is 1. Now that is not technically the final answer, because 1 will divide into both of these numbers. So if the number on the bottom can divide into both numbers on top, then we would just do that division. Negative 9 divided by 1 is negative 9. Negative 5 divided by 1 is negative 5. And we leave the square root 3 attached to the negative 5. So that concludes our discussion on adding, subtracting, multiplying, and dividing binomial radical expressions.